particular video, we're going to take a look at how to straighten data, because if we think about it for just a moment, we realize that out of all the different sets of data that are out there, not everything's linear. There's exponential models in terms of exponential growth, exponential decay, so on and so forth. There's quadratic forms with the data. So if we want to try to start doing things like a line of best fit, or to do the coefficient of determination, if we remember that r squared is the percent of variation explained by a linear model, what we need to be aware of is all of a sudden sometimes maybe we see a data set like this where it looks somewhat linear, but if we look very closely, part of it also looks like we got it's starting to kind of tail off, almost like some type of square root function. So now all of a sudden we no longer have a linear set of data. So what our goal is to get the line of best fit, to try to get a good interpretation of an r squared value, which is again a linear model. What we're going to try to do is take data like this and linearize it. In order to do that, we first want to make sure that it's appropriate to make it linear. So one step, like we can see right here, is to take a look at the data. It looks pretty linear. It looks like it starts to tail off. Another piece of evidence that we can look at is the r squared value. We've talked about that, or the correlation coefficient. And here, this is probably going to be a pretty strong r value, probably somewhere in the high 80s, if not, mid to high 80s, which is, a good indicator of maybe there is a linear relationship. But the best way to really see if we're looking at a linear relationship is by looking at a residual plot. Now, keep in mind, the only way to get that residual plot is after you found the line of best fit. Your calculator, every time you do linreg, it automatically populates a list without you even realizing it. There is a list called resid. So it'll automatically create a list that is residuals. So whenever we want to create residual plots, we're going to take advantage of having that particular list already in our calculator, so we don't have to do any calculations on our own. But in order to populate this list of residuals, we first must run our linear regression. And simply because the line of best fit is what's used to come up with the residuals, right? The residuals was observed minus predicted. So you can't have a residual, the distance from the line of best fit, without actually having the line of best fit. So let's say that we went ahead and did that for our particular data set on the length, or the distance a particular point was from shore, and then the velocity of the river. So we can see we put a line of best fit right there on this data, and it actually doesn't look like a bad fit, even though the data looks like it kind of starts to tail off as kind of a square root function potentially. Again, this is probably going to have, I don't know it off the top of my head, but this is probably going to have a pretty high R value. So those two pieces of data might kind of make us lean toward, hey, maybe a linear model is appropriate. But the best piece of data that we can really take a look at, the most telling piece of evidence, is the residual plot. And as we can see, when we look at this residual plot, we've got a set of data that forms a pattern in the residual plot. That's not what we want for. Recall that residual plots, we want a nice scatter. We don't want any kind of pattern. So there must be a better model out there. Right now, you got to take my word for it. If we do some transformations to this, all of a sudden we get a different line of best fit, right? So here's our original line of best fit, 22.8 plus 0.73x. We do some transformations, and all of a sudden I have a different line of best fit. I've done some math tricks, but now all of a sudden when I take a look at this residual plot, these points are much more scattered. There's not a pattern there. So what I can conclude is whatever transformation took me from the original, which is what you're looking at here, to this new set of data, it was a good transformation, because it's basically, you can see the top of the slide here, it's straightened that data out. We have a much better fit. The residual plot being more scattered, no real pattern, tells us, hey, we have a better fit for our data using this particular equation that we see right here. So what did we do? Our original model was here, and the transform model actually does some work where we're going to end up taking a square root. And why that's useful to us is now if we're going to predict some velocities, Well, we have two equations to use, but as we just saw, this transform model is a better fit. So what we'll do is we'll use that to make any kind of predictions. Plug and chug, we end up right there. So the two most popular transformations and the two that we're going to most likely deal with in this particular course are exponential and power functions. Logs are involved because, with exponentials you have exponents, and to undo exponents you have logs. With power functions, right, this would be things like x squared, x to the third. Again, here we go with exponents, but to undo basically x and y here, as we're kind of picking through those. So power model, parabolas, the x cubed, the x to the fourth, x to the fifth, versus exponential all of a sudden maybe is something like 2 to the x, where the exponent is up in the exponent. Here's a particular set of data. Maybe we say this is number of days, and this is number of bacteria that exist. And if we were to take a moment, do a scatter plot, and put a line of best fit in here, what we should see is that it definitely does not look linear at all. It looks like it's either exponential or potentially that these points right here, if we can just focus on the top part of the graph for just a moment, if we look at this portion of the graph up here, it definitely has an exponential look to it. But just as a heads up, we don't know either, though. This could potentially be part of a parabola if we think about it going back up. This could be maybe part of like an x cubed if all of a sudden we were somehow able to still do some negative number of days and negative number of bacteria. So we're going to try this transformation in terms of some type of exponential function. So right away we can see it doesn't look linear, so we'll try exponential. If we do the residual plot, we can see that's a pretty rough looking residual plot in terms of we definitely can see that there's a pattern in there. And the other piece of evidence that we might take a look at, the R here is actually 0.81, and that's actually a decently strong R value. But this piece right here is about the only piece of information really pointing us toward, hey, maybe this is a linear model. Because when I look at the graph, and then the really, really telling piece of evidence is the residual plot. So we want to make sure that we're consistently looking back at residual plots. The residual plot tells us, hey, linear model is not a good fit. So let's try this exponential. In other words, we're going to take this number of bacteria, and we're just going to log that whole group, do a new scatter plot, which you can see right here. So now we're plotting x versus log of y, and that's much more linear. In fact, it's perfectly linear, probably because we made this set of data up to be a perfect fit. And then as you can see, this residual plot, well, everything's on the line, so the residual plot is 0. But we've got a new line of best fit. So if we look right there, this is our new prediction model. However, with this y, we don't just have y anymore. We have the log of y, or the log of y hat. So if we're going to do some kind of prediction model, we have to incorporate log of y hat. So this is the actual equation from the line of our newly fitted, our straightened out data. Original data, you can see here, had that exponential look to it. So we played a trick. We did log of y, which you can see right here. We took our y, took the log of them, and sure enough, it literally straightened it out perfectly. So we can use this now as a new prediction equation. Plug in 2.5. If it's 2.5 days, how many bacteria? Be aware, don't stop here. We have not solved for y yet. We still have the log of y. We need to go ahead, undo the log by putting it to the 10th power. And so we should predict that at 2.5 days, we end up with 2.828 bacteria. Right. If we were to take a moment and plot weight versus heart rate of these different mammals, what we're going to see is there's the original scatter plot here. And if I took a moment and I did the residual as well, there's the scatter plot, and then here's the residual plot. We can see there's there's some kind of pattern here. There's something that's kind of jumping out at me. There's definitely something happening. So this tells me a linear model is not a good fit. If I'm not mistaken, I believe the R here is something around -0.5, which is not that great of a correlation coefficient anyway. So step one, go ahead and run it through the exponential model, which means we're now doing x versus log of y. Okay? And here, all of a sudden, it starts to straighten out a little bit. It does look like we're taking on a bit more of a linear form, but again, a big cluster of data here. The residual plot, which is kind of the most telling piece of evidence, that's pretty rough. There's not much there. And so although stuff's starting to look a little bit more linear, yeah, I think the R here is somewhere around 0.8, so we're getting closer to linear. I might be mistaken on that R value. But again, the residual plot, the most telling piece of evidence, tells us linear is not appropriate. So we'll try a power model, which means we're now doing log of x versus log of y. And so then all of a sudden you can see now we've definitely straightened that out quite a bit, to the point where almost all those points are right on the line. So it looks like we found our best bet right now with a power model. So log of x, log of y. And you can see now the residuals aren't very big, but there's some above, some below. There's a good scatter. The fact that we don't have a lot of data points is a little bit troubling, but you can see there's less of a pattern to this residual plot right here than definitely to the previous two, right? There's definitely a pattern here, and there's definitely some kind of pattern, some kind of telling piece of evidence there. So it looks like power model is our best bet. One of the things to point out as you go through each one of these models, every time they did a new line of best fit, which means every time you do, you take a log of either x or you take a log of y, they're also going back and finding a new least squares regression line. So here's the best model, this power model, and so we'll use the associated line of best fit to do a prediction, but keep in mind we've now done log of y and log of x, and so we can do a prediction. Humans weren't in my list, so if humans typically weigh about 60 kilograms, we plug in 60. Again, don't stop here. Keep in mind context, right? Heart rate of 1.8 doesn't make any sense. Well, the reason being we haven't finished solving for y. So you do 10 to the 1.883, we realize, hey, a heart rate of 76, that makes a little bit more sense for humans. So in order to create and transform this data, the first thing you want to do, plot the original data, find the least squares regression line, take a look at R, right? Between the original data, taking a look at the scatter plot, taking a look at R, that'll start to kind of tell the story. But the biggest piece of evidence that you want to use as you're trying to figure out, is this linear or is it not, is the residual plot. Remember that you can only do residuals after you found the least squares regression line. Okay, if linear is not the most appropriate model, we're going to try an exponential model. So in other words, we're going to take our y list and we're just going to take a log of the entire list, plot the new data, find the new least squares regression line and write it down. Take a look at the R value again. So now all of a sudden we've got a new graph, we got a new R, and that might start to tell a story, but the most telling piece, again, is the residual plot. Well, here's the thing. Since we got a new least squares regression line, we have new residuals, right? So we need to create a new residual plot. We need to put the new residuals into list 3. So if you had the residuals from step 1 up here, still in your L3, clear them out. Go through the new residuals that you just got after you did step B and number 2. Put your new residuals into list 3. Take a look at that residual plot. Still don't like the fit. Hey, it looks like there's a pattern. I can see something going on. Do log of x versus log of y. Plot the data. Take a look at the R value as you do the least squares regression line. Since we just found a new list rule, if you will, that means we have a new set of residuals, which means we need to repopulate list 3, right? Change L3, right? Clear it out from step 2, go back in, put the stuff in from list 3, check the residual plot to see which one of these has the best looking residual plot, and the best residual plot is the one that has pretty much nothing. And then once you find your most appropriate model, whether it's linear up here at 1, whether it's a exponential model, or whether it's a power model, you want to go ahead and state, hey, the power model is most appropriate. Write down your new least squares regression line. Remember to include logs if appropriate. All right, don't forget about those. It's not just y hat or x anymore. It could be log of y hat. It could be log of x. And then if you're asked to make any kind of predictions, make sure that you solve those appropriately.